Yeah, it's midterm next time.
What?
Come on. What? Not even August. September. Are we on? I think we're on.
Oh, you're laughing now. Really good.
Let's do it. All right, so now we go back to 3 million years ago. So now we're only 3 million years from today. So keep in mind, where did I start? 360 million years ago. I was talking about the Appalachians bumping up against, with Africa, bumping up against each other. Now, only 3 million years ago. Now let's see some things. What do we got going on in these circles? First off, the Mississippi River. And so the Mississippi River, 3 million years ago, it exists. So the Mississippi River, as we know it, as you drew it, and we even got our good friend the Ohio, even our good friend the Wabash. So the Wabash River. All those rivers formed 3 million years ago. However, now let's go to the other circle. What are some things we don't see formed inside the yellow circle? The Great Lakes. The Great Lakes, they ain't formed yet. So the Great Lakes have not even formed yet 3 million years ago. And so they are a very recent phenomenon, 3 million years ago. What else do we not see there? The Hudson Bay. And so the Hudson Bay and the Great Lakes, and our good friend Lake Winnipeg, has not even yet to form. But nonetheless, the Mississippi was already around. And so that's going to be crucial. It's kind of, the Mississippi, it's always been a drain for much of this interior. We can see that 3 million years ago. Water, it goes downhill, and it drains to New Orleans. So 3 million years ago, the Mississippi River was coming plowing into, the water was coming flowing into the Gulf of Mexico. Then, 125,000 years ago, very recently, much of the entire Canada, much of the entire Great Lakes was under ice, under a massive sheet of ice. And to kind of fathom these suckers, when we think about, we've got glaciers that we can see. I don't know if you've been to like Glacier National Park, or you've been to the glaciers up here. These are mountain glaciers. These are nothing like the suckers that are continental glaciers. Continental glaciers are, apart from like tornadoes and maybe some volcanoes, is one of the most violent, one of the biggest eroders of the landscape possible, is a continental glacier. Why? We're talking, at times, a mile thick sheet of ice. So from ground up 1 mile, 5,280 feet, nothing but solid chunk of ice. And not only is thick, it's darn near the entire continent, darn near the entire northern continent. So all of this area here was essentially flattened by the massive power of a continental glacier. However, one of the things that we note and we can tell is that the glacier had a stopping point. It didn't go all the way. It didn't go down to South Carolina, down to Texas, much of the western. They didn't get the Continental Glacier. The Continental Glacier stopped right here in Indiana. And we can go ahead and specifically identify exactly where the most recent Continental Glacier stopped. And we can do that simply by visualizing it here. So what is today Greenland? And so Greenland, everywhere else it's always white. Why is it here not colored? Where? Oh, there it is, there it is. See, Greenland, it's always colored white. And essentially, the same continental glacier that is Greenland, it actually was much bigger and was right here over exactly where we are right now. And so that same exact glacier is now retreated to now, it's kind of ran back to Greenland, but back in 100,000 years ago, actually about 10,000, 12,000 years ago, it was right where we are right now. And so that glacier met all the way down here to the central part of the United States. And so here's its extent. And so it advanced that way, and now it's since subsequently retreated that way. And so one of the things, this is totally sidebar, but for the first time ever, geographers using all these technologies like radar and all this stuff can look through the ice, and they're finding that there's actually all these canyons, all this stuff that they never thought was found there in Greenland. Kind of one of these things that with these new mouse traps that we have, we can kind of check out some stuff that we never knew before. And so kind of the idea is a lot of our we're still learning, a lot of our physical environment, these are things that have actually, most of the things I'm teaching you were learned in the last 200 years. So very relatively new phenomenon. Albert Einstein probably never got the amount of information you just got in that first hour and a half. He had no idea. Anyway, and so I talked about this beforehand. Our good friend, the Mississippi River. What do we need to know about the Mississippi River? First off, it existed before the Great Lakes. It existed before glaciers. However, glaciers very much help to continue to increase the size of the Mississippi over time. So I advanced our glaciers this way, and so that's extended the most recent glaciers. So the glaciers advanced and only went to this part here. One of the things you note, first off, Indiana, for the most part, Indiana was hit with this most recent glacier. But let's go ahead and kind of visualize this once again. I talked about this at the end of the last class, but the Appalachian Mountains used to go all the way down into here. Well, wait a minute, over here, what's this here? The Wichita Mountains here. They were essentially separated, and a large amount of that separation was due from all of that ice. We're talking the entire continent, darn near. All that water has to go somewhere. It just doesn't just disappear. It all flows downhill. And so when we have a massive amount of melting, a massive amount of water coming through this area, of course it's going to find the lowest crevices and cracks and continue to dig deeper and deeper and deeper. And so that helps to understand, well, wait a minute, the Appalachian Mountains have actually been separated from its, I guess it's sibling of the Wichita Mountains over here in Oklahoma and Arkansas. And so here we have kind of a visualization of that. So that's the quick 411 on glaciers. So I just highlighted two rivers. I'll just go ahead and highlight them again. What do you notice about these two rivers? First off, what are they?
Ohio and Missouri.
The Ohio and the Missouri River. So why do we have to learn where the Ohio River was? Why do we have to learn where the Missouri River is? Essentially, can you tell me about it?
Glacial boundaries?
Essentially, right where the boundary stopped is where those rivers formed. And so the Missouri River and the Ohio River are just essentially where the glacier stopped. So, anybody outlet mall shoppers? Any outlet mall shoppers? No? Oh, you are? Edinburgh? You go to Edinburgh?
Yeah.
Is that the place to go? Edinburgh. One of the things you notice is at Edinburgh, you can see pretty much where the glacier stopped. You can see it's very, very flat to your north. You go past the Edinburgh exit on 65, you go past the Edinburgh Outlet Mall, you kind of go up and over, and then it's kind of rugged from there on out. And so it's extremely flat to the north. Essentially what that means is the glacier flattened everything north of Edinburgh, but never went past Edinburgh. Brown County, same thing. So Brown County National Park, wherever the hell it's called, Indiana National, whatever it is, that essentially is where the glacier stopped. And I'm going to try to visualize this as best I can. And so, are these suckers big? These glaciers? How big are they, Andy? No, I'm supposed to ask that question, aren't I? How big are they?
Very big.
Give me some things that maybe I said.
Continental size.
We're talking a continent size, a mile thick sheet of ice, massive massive sheet of you know what. And so it's just going to pulverize everything in its place. It's going to trees, women, children. Of course, they weren't yet around yet, but whatever. So everything, granite, everything in its path, it's going to essentially chomp up into pieces as it continues to bulldoze, in our case, further south to its edge. And so here we go. Essentially, we're going to have all that various stuff, various forms. Some stuff bigger than other stuff, some stuff smaller, some stuff. What are those pretzels? I thought those were crackers. I guess pretzels, chips, sour cream and chai. I can see a few chais. All kinds of battered up, just all bits and pieces of stuff. And so here we got the book, The World is Flat. We should know that the world is actually not flat. It's actually a sphere. It's a ball. But anyway, and so here we have our big old mile-thick sheet of ice. And so it's pulverizing everything in its path. And so essentially what it does is it, let's say, which way do we want the glacier to move? That way or that way?
South.
South is that way, but we're not doing that. I can do that. Let's do south. It's going south. So this glacier is going south, so heads up. All right, so this glacier is heading south. And so it's essentially flattening everything as it moves. It's flattening everything in its path. And then it stops. And then it retreats. And what does it leave behind? And when it retreats, it leaves behind all that stuff, right?
Sediment.
Sediment. And so that's exactly why, if you follow a line from about Terre Haute to Crawfordsville to Martinsville. If you go to IU, just be safe. But anyway, if you go to IU, you're down to 37. You notice this. You're kind of cruising along. It's flat. All that ag, Waverly, Center Grove area. You keep on going, and then you go up, and then you're at a stoplight, and you can see all of the beautiful city that is Martinsville, just right there, right underneath you. You know this, right? There's that one stoplight where you can see all of it down below you, all of that prosperity, all of that. You can see it. Essentially what's happening is here you're driving and you're going up the in-moraine. You're going up this feature that was created from the edge of the glacier boundary. Long Island, New York, formed from the same idea. Glacier stopped, then it went back. What came in to fill the void? Water. And so there's separation. You got Long Island, then you got Connecticut, you got JFK Jr. somewhere in there. Bad joke, I know, it is. Anyway. You can't say it's too soon, though. You can't say it's too soon. Alright, so just leave that there. Alright, we're moving right along. We're learning. We'll hopefully be able to apply this stuff in a future K through 12 classroom, which is kind of why one of our purposes. Alright, where are we at? Let's talk about drainage. Alright, so now I've added to this the other two map quiz rivers. Our good friend the Rio Grande and our good friend the Colorado River. So both of those rivers, they have their origins in either the Appalachians or the Rockies. And so we've got the Ohio that starts in the Appalachians, works its way this way. The Missouri starts in the Rockies and works its way to the same point. So we have these two different rivers that come together here at the Mississippi that are actually bringing with them sediment from two different mountain ranges that are coming together. And that's why essentially everything ends up here in New Orleans. So all of the rivers, all the areas inside this red circle, the main idea, it all drains to the Gulf of Mexico. And so the Mississippi River, the Ohio River, the Missouri River, and the Rio Grande all have their destination all empty out into the Gulf of Mexico. And so the Rio Grande dumps into the Gulf of Mexico. All right, next up, we've got over here our coastal plain. So essentially if I dropped water on this side, essentially it would all go that way. If I dropped water over here, it would all go there. If I urinated, that might help. If I urinated over here, it would all go to New Orleans. If I go to the other side of the Continental Divide, if I go over here, and it would all go to the Atlantic Ocean. Same with up here. So if you're up, any of you from northern Indiana, Portage, where are you from?
Warsaw.
Warsaw, so you're over here. So I don't know where the Continental Divide is in respects to you, but you're pretty darn close to it. So one of the things is all of our rivers go this way, except for up here, the rivers, the St. Joseph and the Maumee go to the Great Lakes. Who else is from up there?
Munster.
Munster. So the cheese, is that spelled the same?
No.
No. So the cheeses up there, the Munster cheeses, right there, same deal. And so all of your rivers flow right into Lake Michigan. They don't flow towards the White River, or sorry, towards the Wabash. So anyone else? I thought, where are you at?
Crown Point.
Crown Point. I don't know where that is.
All
right. So it's a suburb, right? Suburb. So Crown Point, same deal. Your rivers don't flow down here. They all flow towards the Atlantic Ocean. And so if you go down to the other side, everything flows to the Gulf of Mexico. Anyway, and so up there is a little part that actually goes to the Arctic Ocean. So that actually feeds into the Arctic Ocean, that little bit up there. Of course, everything out here goes to the west, the Colorado River. Unlike the Rio Grande, which goes from Rockies to the Gulf, the Colorado River goes from the Rockies to the Pacific via what they call this little Gulf of California down here. Eventually gets to the Pacific. But then you got this sucker here. So you got this area here. What's this area here? Call and response geography.
Great Basin.
The Great Basin. So the Great Basin. What's one characteristic of the Great Basin?
It's like a bowl.
It's a bowl. And so essentially, the rivers here, they all drain to the same point. They all drain to the middle. And so instead of rivers taking sediment to the ocean, everything goes inward. If you don't believe me, there's proof. Everything goes inward. And so everything drains inward. In the case of the bowl, the bottom of the bowl is right there. So the bottom of the bowl, there's a few different examples of the bottom of the bowl, but we know the bottom of the bowl to be the Great Salt Lake. And so the Great Salt Lake is essentially the bottom of the Great Basin. Everything drains toward the Great Salt Lake. All right, so I'm going to ask a rather deep question. Why is the Great Salt Lake salty?
I know. Because of the thing that goes like this, the trench plate goes down and it brings that sediment from the ocean, which is salty, and then it comes up, it boils up in the lava, and boom, there's your salt. Does that make sense? I could draw it maybe.
It makes sense, but it's not true. It's a great answer.
No, it's okay. Usually most of my classes, they tell me, they say, John, don't answer.
John, don't answer.
Most of the GCM people can't read.
Is it because at one point that whole area was underwater, so when the rivers and stuff drain, they take all that salt sediment into that area, so it makes it salty?
Okay. So all the rivers carry with them salty sediment and then dumps into the water body. So why is, what's the lake up in Warsaw?
There's a bunch. Winona, Pike.
The one that everyone gets
Wawasee.
hammered at. Wawasee. So Lake Wawasee, why is it not salty? It's kind of the same idea, right?
But the Canadian Shield has been wasn't underwater for as long as, or as recently as that was.
All right. What other water bodies are salty, other than our salty lake?
Ocean?
Oceans. And so essentially our oceans, just like the Great Salt Lake, very same idea. And so the mountains that were the Appalachians, the mountains that were the Rockies, over time have been eroded away. They've been worn down. What's helping to wear them down? Water. And so what happens is water picks up sediment, breaks it down. Part of that sediment is salt, sodium. And so salt is a part of that sediment that is the same rock here. But over time, water removes that salt and then dumps it here into this bowl. One of the things is, well, why are the oceans salty? Is, think about the salt. Everything, all the rivers flow and bring that salt to the ocean. What we got going on in the ocean is we got something called evaporation. Evaporation, essentially the quick 411 is we got liquid becomes a gas. And so what happens is we have evaporation. So we have all that ocean water. Evaporation then brings up with it water. What doesn't go up with the evaporation? Salt. Salt stays behind. And so when we think about the oceans, why are they salty? Is because all the salt, all the weathering away of material stays there. Whereas rivers continue to take that away. Lakes are freshwater in many respects. What we have up here, where we have Lake Wawasee up in northern India, those are freshwater lakes. Why is the Great Salt Lake salty? It has no rivers taking that salty sediment to an ocean. And so all that sediment, all that salty stuff, just stays there. Evaporation still occurs here, but once again, salt doesn't get brought up with that water. And so when we have water go from liquid to gas, the salt remains. The salt stays behind, whereas the water obviously turns to rain and then comes back down.
Couldn't you say that part of it too is that it's a particularly salty area because you've got salt flats there that are like right next to it.
Salt flats are the same thing. They form from the same thing though, the internal drainage. So all this was just a big sea that's getting smaller and smaller and smaller. So the Great Salt Lake is shrinking. It's slowly but surely getting smaller and smaller and smaller. It used to be much bigger. And so it's essentially, just think about a big bowl of water that's slowly, there's less amount of water. And so with that, the salinity is increased a bit. Anyway, that's the quick 411 on why the Great Salt Lake is salty. It has no rivers to take that sediment, that salty sediment away to an ocean. Essentially, it all drains to the same spot. All right, now let's go ahead and talk about the Great Lakes. The Great Lakes, essentially the Great Lakes were these various lobes. And so as the glacier advances, it advances not as one big book, not as one big straight line, but it actually in waves and lobes, in different groups that kind of come out as out of the same thing, out of the same block of ice, but they come out in different appendages. So these different lobes here help to create the various Great Lakes. And so the Great Lakes are also getting smaller. They're much smaller than what they used to be. But this ice, this has essentially scoured this big bowl from its weight. Keep in mind, a huge chunk of ice, and creates a depression. Over time, I'll actually draw this. hell is this?
It's like soil samples.
I thought it was beef jerky.
All right, let's relate this to. How about let's relate this to a movie? What movie do girls like? They like the Titanic. Yes, Titanic. All right, here's our massive sheet of ice, and so we're looking at the side view, glacier. All right, so we got this massive sheet of ice, and so glaciers. They do not, although I said this, they do not just essentially kind of turn back around and retreat. They don't all of a sudden just say, all right, we're heading back. Essentially what they do is they melt. That's what happens. They just essentially melt. And so this big, huge chunk of ice just melts. How big are these continental glaciers up to? As far as from surface up? A mile thick. We got stuff. Great job. So what did the Titanic hit? Iceberg. So essentially, when we think about an iceberg, it's the same thing as a continental glacier. But these continental glaciers, they break up. And so as they melt, they break up. And so we know an iceberg to be one of these big, huge chunks, but just in the water. We can have these big, huge chunks on land, but the iceberg that hit the Titanic hit was just essentially a big, huge chunk of ice that was left in the water. And so same idea here. So we got this massive, huge chunk of ice that's just essentially slowly melting away. And so now it's nothing like it used to be. Keep in mind, it used to be much bigger. And so this big, huge chunk of ice, is it going to create a depression in the underlying area around it, the underlying surface? A depression. Of course it is. It's a mile-thick sheet of ice. It's a heavy son of a buck. And so here we've got this situation where over time, this chunk creates a bigger and deeper depression. And so it creates a depression. Now this water, it's eventually going to melt. Where's it going to melt into?
The depression.
It's going to melt into the depression it created. And so essentially, what we have created here is a big, huge freshwater lake. Same thing applies to these suckers here. The Great Lakes are essentially a big, huge chunk of ice that creates a depression and then fills that depression with its meltwaters, creating very much the freshwater lakes. So all of our Great Lakes, Huron, Ontario, Superior, Michigan, Erie, Ohio, or Ontario, Hudson Bay, same thing. Hudson Bay is the same thing, although Hudson Bay has been more recently affected by this. The good friend, Lake Winnipeg, same thing. And so these big, huge chunks of ice that are from a retreating glacier eventually create a depression, fill that depression with fresh water, and that's what creates these lakes. And so, do we ever find these lakes in the front of our in-moraine? In front. Keep in mind this in-moraine moves this way. Do we find these big, huge lakes in front or behind?
Behind.
Always behind. That makes sense. The glacier didn't advance any further. And so these big, huge lakes are always going to be behind the glacier. And so in that last 125,000 years, actually, hell, the last 4,000 years, this has been formed. And so the Great Lakes, a relatively new phenomenon. And so Crown Point, Munster, Valparaiso, that actually used to be right on the beach. They used to be right on the coast. So Lake Michigan slowly kind of retreating. So it retreats and it creates the same structures. There's a bunch of sand up there. The same dunes were found further inland where Valparaiso is today. All right, we did that. 12, carry the 1, 12. What time are we out of here? 1:15. All right, let's go for it. Now let's talk about climate. Yay. This whole 3-hour stuff is like, I'm never doing this again. I inherited this class time for those who weren't here last time. This is ridiculous. 3 hours? Are you kidding me? Yeah, is that on tape? All right. Anybody have a 5-hour energy on them?
In my car.
As long as they don't
All right. Climate. All right. So now we've kind of we've provided a good frame for the next part. That's climate. So the underlying structure of the Earth's surface, all that that's underneath this, we've talked about. We've explained in the last 15 hours. Now we're going to focus in on, okay, the more recent, what's actually kind of that carpeted vegetation that's on top of that structure of that base we just built upon. And so climate. Climate is something that's invisible, but you can see the outcomes of climate in the types of vegetation that's found in an area. So vegetation type is a clue as far as the climate that we find in an area. And so although climate, temperature, and I understand precipitation, for the most part are invisible things, we can see by the vegetation type found in an area key differences. And so North America, unfortunately, I wish we would be out a whole lot sooner if we were doing maybe Europe or maybe Australia. Not much variation in climate there. Whereas in North America, we got tropical climates all the way up to ice cap, essentially Greenland and all that there in the Arctic Sea. So we got a whole lot of different climate regions to talk about. So unfortunately, we have to get through them all. And so what I've done here is I'm trying to become more mature in my methodology as far as teaching. And so in the old days, I used to just pass out notes, and we would memorize notes, and I would just sit there and talk to people who are just essentially staring at my notes. So now what I've decided to do at the 300 level is, I don't need notes. I'll just start talking and teaching, and hopefully the notes that you see right there in front of you will follow along what I'm talking about. I hope, and if not, blurt out something that is shown on the notes that I'm not discussing. And so first off, we're going to go ahead and start off in a warm, happy place, and that's our tropical climate region. Where do we find the tropical climate region? To relate to not only our regions, but various specific states. This is going to be, once again, the islands. So we talked about the islands last time as a particular region. This is where we're going to find the islands is going to have a tropical climate. Further south Florida, the Keys, the Bahamas. Did we decide what we're going to do with Cuba or not? Oh, that reminds me. We are going to Cuba this summer one. So if you want to go to Cuba, we're going. I'm not going, but we're going. So we're going to Cuba, which is a once-in-a-lifetime deal. If you have any questions about that, see me afterwards. Here's the tropical climate. The tropical climate, it varies. There's different types of tropical climate, but for the most part, we've got these characteristics. It's really, really warm, and it's really, really moist. It's hot and warm, and it's that way year-round. Further, the day length, pretty darn consistent. And so one of the things is we have a situation where we have like, what, 15 hours of daylight on July or June 20th, and then December 20th, we've got like 6, 7, 8 hours. So we've got a big, huge variability in our day length here. Whereas down here, it's pretty darn consistent. It's almost 12 hours, or pretty close to 12 hours throughout much of the year. So it's very, very hot. That's from a large amount of precipitation, and that makes sense. It's closer to the equator. Further, it's very, very moist here. Well, that makes sense too, because look at all that stinking water around here. And so there's no doubt that this area is affected by all this warm, moist water right off the tip here. Although this is probably not in the notes, hurricane-prone area, but we all know that already. And this area here is the most hurricane-prone next to the next, or one of the next ones we're going to go to. Is there anything from the tropical one I did not mention?
Year-round thunderstorms.
Year-round thunderstorms also. So where we don't really have thunderstorms in the winter, they have thunderstorms all the time. So we really only have summertime thunderstorms, maybe spring and fall here and there, but we don't have winter thunderstorms at all. It's very, very, very rare. There, it's year-round. So there's various reasons for that. We're not going to get to that in this course. So that islands region, South Florida, we find tropical just in the tip there. Just the tip. Oh, I guess also Hawaii too, but we're kind of leaving Hawaii out this semester. Alright, so there is the tropical. Now let's go to the tropical / subtropical desert. So where do we find this? We find this in Arizona, southern tip of California, northern part of Mexico, New Mexico, a little bit of West Texas. So obviously kind of the opposite of what we just talked about. This is going to be an extremely dry area. And so anytime you see the word high pressure, now don't freak out. But anytime you see the word high pressure, think dry. Anytime you see the word low pressure, think wet. So high pressure, dry, low pressure, wet. And so in that description, you probably see dominated by the subtropical high pressure, dry. And so it's a dry air mass. And so then, go figure, we don't get a lot of rain here. It's heavily influenced by a high pressure, a dry air mass that essentially sits over this area for much of the year. And so other characteristics, we get very, very hot days, very, very, very cool nights because there's no clouds. Clouds do a good job of blocking sunlight, so that would prevent the heat from going really, really high during the day. But because there's no clouds, the temperature gets really, really high during the day. Similarly, there's no clouds at night. Clouds do, just like last night, if you're cold, you put on a blanket to trap your body heat in. Clouds do a good job of trapping in that heat. When the clouds aren't there, that heat can just go right through their atmosphere, and it can be quite cool. And so if you've been to the Middle East, same thing. What else do I... Anything I didn't say about the tropical/subtropical desert? I conquered it. Moving right along. Where are we going to now? Humid subtropical. And so if you think about Florida, other than that little tip of Florida, all of Florida is humid subtropical. We can almost relate this exactly to Dixie. The Dixie region is essentially humid subtropical. And so as far as the southeast of the United States, or what we refer to as the South, the dirty South maybe. So this entire area here we refer to as being humid subtropical. What that means is we get a little bit more variability in the weather. We get a little bit more of a cooler winter, a little bit of a cooler summer as well. It's not as stinking hot as the areas to the south, the tropical areas to the southern tip of Florida. But the name implies humid subtropical, humid. That means it's wet. So this is an area of our country that gets a good amount of rainfall. And so if we can kind of combine the two areas among one more, we're going to come back to that one, that get a ton of rain, it's going to be the tropical and the humid subtropical. Here, a ton of moisture, and that makes sense because there's a lot of water right here, whether it be the Gulf of Mexico or the Atlantic Ocean there. And so this area here is influenced heavily by warm, moist, tropical air. Anything else I need to say with that one?
What is MT, air mass?
Yeah, MT stands for moist tropical. So now you know. So now you can with your little pencil or pen, circle MT and say moist tropical. Actually means maritime tropical. We're just going to say moist because we know what moist means. Anything else I need to hit on that one? Right here, huge hurricane. Hurricanes, these two right here, are the hurricane core of North America. In fact, one of the most heavily hit areas. Anybody from Taiwan? Taiwan's got the claim to having the most amount of hurricanes coming through it. Anyway, where are we going now? My favorite. Next up, the Mediterranean climate. The Mediterranean climate, okay, the humid subtropical. It's always found, I don't know why, but it's always found, I do know why, but I'm going to tell you. It's all found over here on the southeast side of continents. So the southern and eastern side of continents, we find the humid subtropical. So go to China. In the southern and eastern part of China, you're going to find a humid subtropical climate. Now, on the southern and western side of continents, for the most part, we've got a Mediterranean climate. So Mediterranean climate we find in the southern and western parts. And so Europe, the southern and western part of Europe, Spain, southern France, Italy, same climate, Mediterranean. So the key characteristic with the Mediterranean climate, first off, its key characteristic, wet winters, dry summers. Wet winters, dry summers. Wet winters, dry summers. So that's the key, wet winter and dry summer. Why is it dry in the summer? Is because in the summer, it then becomes affected by a high pressure. And so high pressure, dry. During the winter, it's affected by low pressure. And so we can understand how it varies, high to low. And so during one time of the year, low pressure goes over the area, bringing with it wet winters. But then in the summer, a high pressure moves over the area, bringing dry conditions. Mediterranean. And so what are they known for in Napa Valley? What are they known for in Italy? Grapes. Grapes. And so why do grapes like growing in those places? Grapes, what they do is over time they've adapted to survive the dry summer. So how can vegetation survive that dry summer without water? It just essentially stores in its fruit. And so it gets through the entire dry summer period by storing water in its fruit. Bite into a grape. Is it juicy? It is, because that water is being stored in the fruit. So grapes grow very well in those climates that have a wet winter and a dry summer, which explains why wine grows so productively in this area. Southern California, Mesoamerica to the coastal part of Mesoamerica would be associated with Mediterranean climate. So California is very much affected by that. Not all of California, but a good amount of southern and central California is affected by that dry summer period. Anything I didn't mention?
No, you covered it.
You're I guess, our go-to person, just because of where I'm standing. All right, where are we off to next? All right, moving right along. Next up is the marine West Coast climate. Marine, what do you think marine might mean?
Ocean.
Ocean or water, coastline. What do you think West Coast means?
The coast on the west.
Oh, you guys, I'm telling you, 300 level, I'm just impressed with this, this talent, right? And so here, along the West Coast, we have a particular climate region. Guess what? We don't find this anywhere on the East Coast. Where do we find the marine West Coast climate? Other places in the world? Europe. So how in the world, here's basically, London's about this same latitude. It's way over here, but London's about this same latitude. We're talking, damn, that's, I mean, we're talking north of Edmonton. London is way up here. How can people survive in London with it being so latitudinally north? How can it be so stinking? Oh, it's on the west coast of the continent. And so one of the characteristics of the marine West Coast, it helps to lessen the change in temperature. The lows don't get as low, but the highs don't get as high. And so the marine West Coast climate, compared to the other climate regions, not much change in temperature. The winter might get cool, but it ain't going to be freezing cold. But same way, the summer, it's going to get warmer, but it ain't going to be stinking hot. And so the marine West Coast climate. Further, the marine West Coast climate is characterized, in our case, by a good amount of precipitation. So what we got, that makes sense. We got all this water here. All this water here is going to no doubt affect the climate, the air in the area right next to it. And so this area here is quite moist, but like I said, not much change in temperature. You know this, Vancouver. Vancouver, how many months? Vancouver's in Canada. America Junior. How many months per year does Vancouver average below freezing? Canada, way up here. Or sorry, Vancouver, way up here. How many months of the 12, so give me 1 through 12, how many months does it average below freezing, 32 degrees, or whatever it is in Celsius? It's way up here. Zero. They never have any, very rarely do they get below freezing. And that's because of the influences of the nearby water body. So marine West Coast climates have that characteristic. Anything I didn't mention?
Two things. The NP air and the Appalachians section.
All right, NP air. What does that mean? That means moist and polar. So essentially, what that means is it's wet, but it's cool. Polar things, polar bears, they're cold, right? And so NP is moist, polar. So just think of it being cold, cool, and moist, cool and wet. The Appalachians, why are the Smoky Mountains smoky? It's not because people are burning anything. It's not because natives decided to set it all on fire and said, oh, Smokies. No, it's because it kind of has that mist. It looks like it's smoking. It looks like it's smoldering. But essentially what that is that's just a mist. And so it's very similar to what we would find over here. And I'm not going to get too much into the Appalachians. You don't need to know it. Wipe it off. An old relic from a previous lecture note. We're moving right along, aren't we? I got a feeling we'll let out early still. I got a feeling. What do you know? All right, now we get to go home. Now we get to go where we are here. So this is what we call a humid continental climate. Humid continental. So first off, humid means it's going to be wet. And so we know this. The places out here in the eastern part of the United States, much wetter than the areas over here, which are much drier. So the areas here have much more dry conditions compared to here. We're much more wet. And so, of course, it's going to relate to agriculture, for sure. We're going to definitely see that play out here. All right, Humid Continental. I guess I'll work from the bottom of the notes up. What do we find here? We find the breadbasket region. We also find the Foundry, but also New England. And so New England, Foundry, and the breadbasket are all parts of the Humid Continental climate region. Humid Continental climate region. So here we're going to have very cool winters, cool to cold winters, and hot summers. And so here, remember, we just came from the marine west coast. Not much change in climate. The highs don't get too high, the lows don't get too low. Here in Indiana, it gets stinking hot in the summer, doesn't it? And it gets stinking cold in the wintertime. And so Humid Continental climate is going to have much more variability between the highs in the summer and the lows in the winter. And so much bigger temperature extremes. I can explain that, and I'll stick around later afterwards and explain it. But places further inland have higher extremes in their temperatures. The highs get much higher, but the lows get much lower. Case in point, where do we find some of the highest temperatures ever recorded in the United States? Right here in Texas, right here in the inland areas, because in the summertime, it gets really, really, really hot right here. Whereas places along a coastline are more moderated by the nearby water bodies. And if you don't get that right now, I can explain it afterwards more in depth. Not too critical. Other things that I didn't mention.
Lots of weather change.
Lots of weather change here. And that's the whole saying, it's stupid, I hate the saying, but if you don't like Indiana's weather, wait 2 minutes or something. I hate that thing. But it's for the most part true. You compare it to Florida, every single day it's hot, every single afternoon they get a thunderstorm, it's pretty much all the same. We're in Indiana, we know we can have big swings. Huge heat wave like we had this week. Then like, what, 2 weeks ago, it was cold. I mean, it was like lows in the 50s. So here we've got changes in temperature changes, and that's largely because we've got these migrating low pressures. So we have these low pressures, once again, low pressure, wet, these migrating low pressures that come through this area, bringing with it changing conditions. So migrating low pressures that move and bring with it changing weather. So where the other places much more consistent, here now we're getting to more changes in the climate over the course of a year. Very, very high highs temperature-wise, very low lows in the wintertime temperature-wise. Moving right along.
Yep.
Why not? Next up is this area here. So this is essentially much of the empty quarter, much of the Great Plains, we could say, or half of the Great Plains, and the Great Basin here. And so it's what we're going to call Semi-Arid Step. So essentially the whole idea is steppe. It's spelled funny, S-T-E-P-P-E. But just go ahead and take off the excess P-E, and it's the same idea, steppe. And so this is a step from the humid climates to the drier climates. And so we've got our dry and our wet, that kind of step, that transition in between is going to be this area right through here. And so it's got a little bit more variation, it's got a little bit more moisture than the dry areas to its west, but not as much rain as the areas further to the east. And so it's kind of in between. So Nevada, Las Vegas is in the semi-arid steppes. If you've been to Vegas, you know it's kind of dry. It's not super tropical. It's not super hot. It's not a miserably hot desert. It can be, but it's more going to be lumped in here with places like Utah, but not this area right through here. Why? What's going on here, I ask? Rocky Mountains. And so mountains completely can change climate. And so these areas are all pretty consistent because there's not much change in the topography, but then you stick the Rocky Mountains in the middle of it, it changes things. The quick 411 here. Mountains. Here we go. Concepts at work here. Learning in action. Here's a mountain. Here's the top. Temperature. As we go up, does it get warmer or does it get cooler? Colder. We know this. The top of the mountain is much colder. And so mountains completely change things. Whereas everything's all nice and hunky-dory here, when you have a mountain, that's going to completely change the climate. And so you might have a mountain stuck in the middle of, for instance, I kid you not, Hawaii has a mountain that's so tall that the top of it gets snow. Hawaii gets snow. Right through the middle of Africa. there's a mountain called Mount Kilimanjaro. I mean, it's like feet or a few miles from the equator. Mount Kilimanjaro, a few miles, it's right there in the middle, but it has a snow-capped mountain. And it's the rule of elevation. If you get high enough, the temperature is going to get much cooler. And so essentially, the quick 411, the further away you get from the surface, the temperature goes down. And you can know this if you ever go up in the air for some reason. Where are we at now? Oh, there's our mountains. And so that's essentially, mountains do a good job. I don't know if it's going to be here. Yeah, it is going to be here. Great. So now I got to go through the last difficult concept we're going to talk about today. So what did the mountains do? The mountains do a good job. We've talked about the mountains. There's a reason why in the map quiz I identify the mountains. The mountains do a good job of distinguishing and separating climate type in the United States and North America. So we've got these mountains. These mountains pretty much go right up the side of them.
Yeah.
What's up? I'll slow down. Do I need to speak up? Do I need to talk louder?
No, you're okay.
Okay. So here we have the mountains here. So on one side, quite wet. On the other side, quite dry. And so let's get through this very difficult concept. So we're going to talk about a term. Might as well get to know this term, orographic. Orographic. So what you can do is on the way home, or tonight when you're at the club, you can tell people that you learned today in geography how to make it rain. In geography, you learned how to make it rain. So take that to the club tonight. So let's do it. For the most part, we've got this situation in which weather, wind, everything goes this direction. So it goes west to east. We know this. She's going to be back. I can't wait. September 3rd. Who's back? Who's back in town? Who's back on the air? She's back. I follow her on Twitter.
Your weather lady, what's her name?
Angela Buckman. Angela Buckman, my favorite meteorologist. She's back. She's been gone for a year. She's back. When she comes back, you're going to watch her on the news. And when she's giving you the forecast for Indiana, she always is kind of saying, well, here's what's happening in Iowa, or here's what's happening in Illinois, with the idea that stuff's all going to be working its way this way. They never really tell you what's going on the East Coast. They tell you what's happening over here, because our weather goes west to east. Okay, so that makes sense. So we got all this water here, and we got this air that moves west to east. And so this air is going to be picked up because of evaporation, and it's going to be moved along this way. But then all of a sudden, something gets in its way. Something gets in the path of that west to east pattern. And that's our mountains. And that's orographic precipitation. And so here we go. And so once again, I'm showcasing that west to east pattern. For the most part, that's what characterizes North America. A west to east pattern as far as the weather. That's why we're always looking to the west to see what it's going to be, for the most part, come the next couple days. All right, so here's orographic. And so here we have a mountain. And so the key idea here is how to make it rain. Here you go. How do you make it rain? Tell everyone tonight. You get warm, moist air to rise. If you can get warm, moist air to rise, warm, moist air, if you can get that warm, moist air to rise, eventually that warm, moist air, if it rises, what's going to happen? That warm, moist air, is it going to heat up or cool down? Cool down. It's going to cool down. And so that warm, moist air is going to cool down. And so essentially, that gas, that water vapor, eventually is going to get too cold, right? It's going to cool down so much that it's going to form ice droplets. Those ice droplets are rain if they fall down to the ground. And so those ice droplets eventually get too big, they can't be held aloft. And so warm, moist air, if you can get warm, moist air to rise, that warm, moist air that's going to rise is going to condense, it's going to cool, and it's fall back down as rain. And so we get warm, moist air to rise. We're going to eventually get to the point where it gets too high, eventually it condenses, cools, and comes back and falls down as rain. And so we can get that in various forms, but let's do the easiest way. Let's stick something in the path of that warm, that moving air and force it up. And so we stick something in its path, we'll call it a mountain. And so that warm, moist air pocket is going to be forced up, and eventually it's going to cool, condense, and fall down as rain. And this is why the western edge of the North America, whether it be the Cascades, the Sierra Nevadas, the Coast Ranges. That's why those mountains on the west side are super, super lush. A huge amount of precipitation. If you don't believe me, Seattle, what are they known for? Other than coffee and suicides? Rain, which are kind of maybe the same thing, kind of related because, no, I don't know. Actually they are, because it constantly has a mist. They constantly have rain there, because Seattle's right here. And so it's always, if you think about the Cascades, or just a little further to its east, it's always getting that rain, which is why they drink coffee, because at 9 in the morning it looks just like it does at 5 o'clock in the afternoon, and because it's always gray there. So drinking coffee, and then suicide rates are actually similar too, because it's always dreary. It's the same thing in the British Isles as well. Anyway, and so now we just learned how to make it rain. We kind of talked about one side of the situation. All right, and so here we have this warm, moist air mass. It kind of comes in contact with this mountain, it's forced up, it gets to the top. This is the best way I can describe it. It spews out all of its fluid. That's the way I can describe it. And so essentially it has no more water left. And so essentially it's rinsed itself, it's sponge. I'm doing the dishes. So it's sponge. It just essentially all that water's come out. Now that sponge is dry as a carrot. It has no more water left as that air pocket continues on. And so when it continues on the other side. It has a situation where now the other side, the air is continuing. It's not stopping. It's just going up and over. But now it's dry. And so that's why on the other side of the Cascades, on the other side of the Sierra Nevadas, on the other side of the Rockies, the eastern side, it's super dry. And so essentially much of the western part of the United States has had this situation where the mountains along the coast, which we talked about before as far as how they were created and why they're on the coast, have done a good job of helping to dry out essentially much of the interior. The semi-arid steppe climate and the Great Plains for sure have been affected by this process. Does this make sense? Cool. So right through here, the Cascades, and so we've got two different places. Seattle on one side, very lush, tall trees. What did Kermit say? Kermit's famous line, Kermit the Frog? It ain't easy being green. And so to be green, it requires a whole lot of either sun or rain. And so in this case, rain. And so Kermit, he's not here because there's not enough rain. It's super dry here on the other side of the Cascades. So Seattle, this is Walla Walla, Washington. One of my favorite cities to say, Walla Walla, Washington. All right, so there's our precipitation. I show this to ask you, do you see an example of orographic precipitation, or I should say this, let me step back. Do you see mountains? Wait a minute, this is a map of precipitation. How the heck am I going to see mountains? But do you see any mountains? If you do, tell me where. Just yell it out loud and tell me where to go.
In Dixie, there's the path.
Huh?
On that side right there, up down where the green.
There?
No.
Northwest side.
Okay, we already talked about that one. Yeah, so we see the coastal range, we see the Cascades. Sierra Nevadas right there. We can see the Sierra Nevadas. We can see that coastal range right there. We can see the San Joaquin Valley. We can see all that. We can see the subtropical desert, the dry areas. We can see that key difference. Blue being a lot of rain over here. Orange being hardly any rain. And you can see that kind of that separation here. So then there's Rocky Mountains. Go ahead.
Oh no, I was saying because Idaho, is that part of that's part of the Rockies, right?
Yep, Rockies, right through here.
Okay. So there's just little pockets where there's.
Yeah, those are going to be probably the peaks, the high points.
Okay.
So there's the high points for sure, and it's going to be on this side. So I guarantee the mountain goes right through here probably. Here's right through here's the, it's going to be on the western side of these slopes.
See where in West Virginia, like right where what's left when the rains come through the Midwest stops.
Yeah, so we won't really talk about it here, but they've got here, this area of the country is heavily affected by air coming up. So this air comes up, and this air is from the Gulf, so it's going to be warm and moist. It comes up this way, and it comes in the back side of the Appalachians. That's why the Smoky Mountains are over here on this side of Tennessee, is because this warm, moist air comes up the back side, and then we got orographic happening there. So that's why we have a similar climate here in the Appalachians as we do there. For those two of you who could follow that, which is fine. Anything else you want? I can pick this apart. Oh, there's some more mountains up there. Where are we at now? What's next?
Subarctic.
Subarctic. We got 2 more left, right?
Yeah.
All right. We'll be out in 5 minutes. Hell yeah. All right. Here we go. What we got? I just got excited. I forgot. Subarctic. All right. Subarctic. So characteristics of the subarctic. First off, the subarctic. This is going to be. This climate region is essentially over the same area that we find what we call the Boreal Forest. So the subarctic, do we find the subarctic in the United States? Where?
Alaska.
Alaska, that's it. So subarctic is overwhelmingly going to be something we find in Canada. Apart from the little bit up there, that's Alaska. And that's the only, that's not really continental United States. That's kind of a whole different deal up there. So nowhere in the United States do we have subarctic. But subarctic corresponds with what we call the Boreal Forest. Boreal Forest, essentially, Christmas trees. Tons of Christmas trees is the Boreal Forest. So it's nothing but what we would think of as our nice pine trees. So we don't see many deciduous trees, trees that lose their leaves. We don't see colorful foliage up here in the subarctic. It's heavily evergreen trees. Why? It's pretty much cold year-round. And they don't get a lot of precipitation either. So it's fairly cold and dry. But the key here is very, very cold, very long winter, and a very, very short summer. But the subarctic area, Canada, Boreal Forest, what else is there?
Just basically the tree line's the end of it.
Oh, right. So the northern end. So it's extend up here. This is essentially where we stop having trees. So you can't grow any trees. Trees don't grow beyond that. Why? Trees need more sunlight. Kermit said it. It ain't easy being green. So for up here, there's not enough sunlight, not enough moisture for trees to grow. So up there, the next one, we don't have trees. And so the northern extent of this line is where we have the end of what we call woody plants. So trees stop there. We call that the tree line. This is the tree line, right through there. Yeah. Good?
Yep.
Right on. Moving to our very last one right here. This is the frozen tundra. So this is up in the northern part, northern part of North America. All you would find here are grasslands. So if there's not ice, it's going to be grasslands, very, very short grasslands, maybe some bushes here and there, some very, very small little plants. You're not going to see big trees here at all. And like I already mentioned, the reasons why. This is also up in an area of the continent in which they have extremes in day length. And so they'll have periods of a week or two in which they'll hardly get any daylight. Whereas then they'll have other parts of the year where they'll get 24 hours of daylight. So huge variation in day length up in this area of the continent. But like I said, extremely cold. Not much lives here because it's so darn cold, so darn dry. So here's polar bears, kind of. This is their area. This is where they take over.
High snow and glaciers.
Yeah, high snow, high amount of snow. Wait a minute, Andy. You just said it's quite dry. Why is there a high amount of snow? Is because the snow doesn't melt during the summer. And so it's such a cool summer that the snow from last winter sticks around and makes it to the next winter. So that's what we call permafrost, I believe. I call that permafrost. I don't know, is that in there?
Yes.
Permafrost. Permafrost means the ground's frozen year-round. So this is an area where the ground is, it might have just a few, down in the southern part, just a few, a week here and there that can actually grow some stuff. Anything else in that one?
Glaciers.
Oh, glaciers. And so if we think about our good friend, the Continental Glacier, that once was way down here, is now way up here in Greenland. And so this area here was most recently affected by glaciers. So this glacier is slowly working its way backwards. And so, tell Al Gore that this glacier has been melting way before humans were around here. And it's still going to melt. Nothing we can do about it. So this area here is quite flat. And also where we find all these lakes here. Keep in mind I explained earlier how the lakes form. And so there is a ton of lakes up in this area of the continent. We got through it. We did it. And, all right, yeah, and for next time. See the forums, but you